Bismillah ar-Rahman ar-Rahim. This video is about the distribution of the kth largest random variable among n i.i.d. random variables. We have random variables x1, x2, all the way to xn. They are i.i.d. We are interested in the CDF of the kth largest random variable among those n random variables. Note that if k is equal to 1, then x with this subscript 1 is the maximum of those random variables. And if k is equal to n, then x sub n, this is the minimum of those random variables. We will obtain the CDF first, and this is applicable to any type of random variable, but then we will be specific and assume that our random variables are absolutely continuous and they have a common PDF, which is this small f. Let's start first by the CDF. To be exact, we will start with the complementary CDF. What is the probability that the kth largest random variable is greater than alpha? So this is the complementary CDF, and this event is the event that at least k random variables among those n random variables, at least k of them are greater than alpha. If we arrange those random variables in an ascending order, then perhaps this is x1, this is x sub 2, this is x sub 3, and so on. This is x sub n. This is if we put them on the number line. The event of interest is that the kth largest is greater than a given alpha. Suppose that alpha is this number here. What does it mean that the kth largest is strictly greater than alpha? We must have at least k of the random variables with values that are greater than alpha. Because if the kth largest is greater than alpha, then it must be the case that x sub k is somewhere here. We must have at least k of the random variables greater than alpha. Let's convert this probability into a summation. We will sum over all the possibilities in which we have k or more random variables greater than alpha. Our sum has an index small m from small k all the way to n, which is the total number of random variables. So the event here, which is the complementary CDF of x sub k at alpha, this probability is the summation m from k to n, the probability that exactly m random variables among our i.i.d. friends here, exactly m random variables are greater than alpha. What is this probability? We have n i.i.d. random variables. The probability that exactly m of them are greater than alpha. From those n, we will choose small m, and then those small m random variables are greater than alpha. And this happens with a probability 1 minus the CDF of the random variables evaluated at alpha, because this is the probability that one of those x's xi, and they are all identically distributed and they are independent, probability xi is greater than alpha. And then the remaining random variables, the remaining n minus m random variables, are less than or equal to alpha. So here we have the CDF big F of alpha raised to the power big N minus m. This is the complementary CDF. So 1 minus this summation will give us the CDF of the kth largest random variable among those n i.i.d. random variables. In summary, we write down the complementary CDF, the event that x sub k exceeds alpha. This means that at least k random variables are greater than alpha. Then we can do a sum where the index of summation small m goes from k to big N, and the events for which we compute the probability are that exactly m random variables among our collection of n i.i.d. random variables are greater than alpha. Now this probability is n choose m. We are choosing m random variables from those n i.i.d. random variables, and then we need small m of them to be greater than alpha. So we have the complementary CDF raised to the power small m, and then the CDF raised to the power big N minus m. If we further assume that our random variables are absolutely continuous and they have the PDF small f, we can now obtain the PDF by differentiating the complementary CDF and multiplying by -1. So our next step is to assume that the random variables are continuous. We compute minus the first derivative of this probability with respect to alpha. We are differentiating a finite sum, and so we can just differentiate term by term. Inside the summation, we have two functions of alpha. We have 1 minus f of alpha to the power m, that's one term, and then this is multiplied by f of alpha to the power big N minus m. We can apply the rule for differentiating the product of two functions. So here we have a term in which we differentiate first with respect to this guy, keeping this as a constant. So this one, here it is. And then if we differentiate this guy, then we get m. So when we take the derivative with respect to alpha, we get m. And then the bracket will be raised to the power m minus 1. And then by the chain rule, we need to differentiate what is inside the bracket. We have 1 minus the CDF. So the derivative is minus the PDF. we are computing the derivative with a minus sign, so we get f of alpha. Then we fix this guy, and we differentiate this with respect to alpha and multiply by minus 1. So we get this here, and the power is reduced by 1, and the derivative of the CDF is the PDF. The PDF, f of alpha, is common. We can take it outside the summation. We have here n choose small m. We will take the complementary CDF raised to the power small m minus 1, and the CDF raised to the power big N minus small m minus 1. The remaining terms from here, we have small m, and because the power here is n minus m, then we have here the CDF minus, and then this guy, big N minus m, and here we have 1 minus f of alpha, because outside we have to the power m minus 1. Let's focus on this bracket. If we expand, we will find that there are two terms that cancel one another, and we are left with this expression here, which can be written as small m minus big N as a common factor, and between brackets we have 1 minus big F of alpha. So this is the PDF of the kth largest random variable, assuming that we have started with an i.i.d. absolutely continuous random variables. Can we actually simplify this expression? And the answer is yes. Let's replace big F of alpha by eta, and let's investigate a sum that looks like this. It's like our sum without this outside PDF, and it is just that the CDF is written as eta. Eta is a number between 0 and 1. Can we evaluate this summation in closed form? Let's start by isolating the term in this summation in which small m is equal to big N. So here we will get big N choose big N, that's 1 minus eta to the power big N minus 1. Then if small n is equal to n, we get eta to the minus 1, and from this bracket we have n minus n plus n eta. These two guys go, and we have eta times eta to the minus 1, that's 1, and we have this big N times 1 minus eta to the power n minus 1. This is the term coming from here when the index of summation small m is equal to big N. Now we split this term. So we write m and then minus n, 1 minus eta. If we take this guy here, we have big N, n choose m, 1 minus eta. Now when we multiply these, we get to the power m, and then eta to the power big N minus small m minus 1. Then we have a minus. What about the first term? We can manipulate this small m when it is multiplied by the binomial coefficient. Small m times n choose m, that's n factorial, over m factorial n minus m factorial. M divided by m factorial, that's m minus 1 factorial. N factorial can be written as n times n minus 1 factorial. So we have n, let's write it here, n, and then we have n minus 1 factorial divided by n minus 1 factorial, and this n minus m can be written as n minus 1 minus between brackets m minus 1, and then we have factorial. This is exactly the binomial coefficient n minus 1 choose m minus 1. Then we have the terms 1 minus eta to the power small m minus 1 and eta to the power big N minus small m minus 1. We can take big N as a common factor, and this is what we have right now. The next step is to take this binomial coefficient n choose m and use the known formula for binomial coefficients, that n choose m can be written as n minus 1 choose m plus n minus 1 choose m minus 1. The binomial coefficient n minus 1 choose m minus 1 is multiplied by 1 minus eta to the power m minus 1 eta to the power n minus m minus 1. And then after doing this change here, we have minus, and we take these two terms, 1 minus eta to the power m, eta to the power n minus m minus 1. We can take 1 minus eta to the power m minus 1, eta to the n minus m minus 1 as a common factor, and then we are left with 1 from here and 1 minus eta from this part. And this is eta. Eta can be combined with this eta, and we can write eta to the power n minus m, or I can write it in this way, eta to the power n minus 1 minus between brackets m minus 1. When we did this change, we have this binomial coefficient. Here it is multiplied by these two terms. This is exactly what we want. We have here an expression that depends on m. Everywhere m appears, it is m minus 1. It's n minus 1, it choose m minus 1. 1 minus eta to the m minus 1. Eta to the n minus 1 minus between brackets m minus 1. This is exactly the same expression, but m minus 1 is replaced by m everywhere. We can now telescope. If we have sum m from k to big N minus 1, g of m minus 1 minus g of m. What is this summation? It is g of k minus 1 minus g of k, if the index of summation is equal to k. When the index of summation is k plus 1, we get g of k minus g of k plus 1. Then we get g of k plus 1 minus g of k plus 2, and so on. As we can see here, those terms will cancel. The last two terms will be g of n minus 3 minus g of n minus 2. This is when small m is n minus 2. And then finally, we get g of n minus 2 minus g of n minus 1. These two cancelled, and this one will be cancelled by a previous term. We have two surviving terms. The first term is this expression here with m replaced by k and minus. The second surviving term is this expression here with small m replaced by big N minus 1. This is exactly how we get these two terms. We take this one, replace m by k, and then the minus sign. We take this one, replace m by big N minus 1. When we do this, get here n minus 1, choose n minus 1. This is 1. This term is minus n times 1 minus eta to the power n minus 1, which is exactly this term, but they have different signs. These two terms go away. We are left with n times n minus 1, choose k minus 1, then 1 minus eta to the k minus 1, eta to the n minus k. Now we can write down an expression for the PDF of the kth largest random variable among those n i.i.d. random variables x1, x2 to xn. The PDF is f of alpha, and then we take this expression and write it replacing eta by the CDF. Here is a shortcut to write down the PDF of the kth largest random variable directly. We are interested in the PDF of the kth largest random variable among n i.i.d. random variables from x1 to xn. Those random variables, they have PDF small f and CDF big F. The PDF of the kth largest is one of the n random variables is the kth largest. From those n i.i.d. random variables, one of them will be the kth largest. So we have an n. This is like n choose 1. One of the n guys is the kth largest. Then we multiply by the PDF f of alpha. To be the kth largest, there must be k minus 1 random variables among the n random variables with values that are greater than alpha. From the n random variables, we have chosen 1 to be the kth largest. That's this big N here, or n choose 1. From the remaining n minus 1 random variables, we choose k minus 1. Those will be random variables with values that are greater than alpha. The probability that one of those random variables is greater than alpha is 1 minus big F evaluated at alpha. This is the probability that a random variable is greater than alpha. We have k minus 1 of them, and they are independent. So we raise here to the power k minus 1. What about the remaining random variables? We have n minus k remaining random variables. Those should be less than the kth largest random variable. So those should be less than alpha. We put here the CDF evaluated at alpha. We have how many of them? N minus k. One random variable is the kth largest. K minus 1 random variables are above the kth largest, and the remaining n minus k random variables have a value that is less than alpha. We can also write down directly the joint distribution of the kth largest and the k plus 1 largest random variables. This joint PDF is equal to 0 if beta is greater than alpha. So we want alpha to be greater than or equal to beta. From the n random variables, we need one of them to be the kth largest. We have n choices. From the remaining n minus 1, one of them will come in rank after the kth largest. This will be the k plus 1 largest. So we multiply here by n minus 1. Then we multiply by the PDF evaluated at alpha and the PDF evaluated at beta for x of k to be the kth largest. And since we are writing this joint PDF with this parameter alpha, there must be k minus 1 among the n random variables that are above alpha. So we need to choose k minus 1. One of the random variables is the kth largest. Another one is the k plus 1 largest. The remaining ones are n minus 2 random variables. From those n minus 2 random variables, we choose k minus 1. Those must be greater than alpha. We put here, like this term, 1 minus f of alpha, all raised to the power k minus 1. The remaining random variables must be less than beta. We have f of beta, and here we are talking about n minus k plus 1 random variables. K plus 1, this is because there are k minus 1 random variables above alpha. Then there is the random variable x sub k, and then there is the random variable x sub k plus 1. The remaining random variables, n minus between brackets k plus 1, those guys must be less than beta. This is the joint distribution of the kth and the k plus 1 largest random variables among n i.i.d. random variables that have PDF small f and CDF big F.